Now let's check that we can also compute the distance from any vector or any point to the decision boundary. And we will see that this distance can be computed as the evaluation of that vector in the decision boundary divided by the magnitude of our parameter, our vector of parameters. I am going to show this in the next slide, but here it is important to see that this distance, even though we are not using that distance in our current simple model, the logistic regression, it is a very important distance, and this is very useful when we apply support vector machines. We're going to study that later on when we get into support vector machines, but this is a very good moment to see that it is possible to compute distances from any point to a decision boundary. In this example, we're talking about points in a two-dimensional space, x1, x2. And our decision boundary is a line, but this scales up to any dimension, so it scales up to any hyper space. So let's see how we can compute this distance from the point x to the decision boundary. First, consider that we have this vector here in brown. It's a vector that is exactly lying on the decision boundary. So we have this vector here, and we are also going to need this black vector, which is a vector going from this point in the decision boundary. It's orthogonal to the decision boundary and goes exactly to the end of the vector x. So this vector in blue that I've written here as in color blue equals the brown vector plus the black vector. Okay, this is just the sum of two vectors. Brown plus this black equals the vector in blue. So we know that this is true. Okay. Now, if we evaluate both points in our decision boundary, we will write this and this here. It's just considering this expression as a point. We need to multiply by the vector parameters and then add the bias. From this, we know that this is simply the evaluation of x in our decision boundary, and here we can simply multiply this w by x and this w by this expression. Okay. And in the next step, we can simply move w0 to the left, and here we see that this is the evaluation of this vector that is in the decision boundary. So every point that is in the decision boundary has an evaluation of 0. So we can simply delete this, and then we have that the evaluation of x equals this r times this expression here. Now it is important to see that this r, we are considering r to be the magnitude or the size of this vector, this black vector, which is exactly what we want to compute, the distance from this point to the end of vector x. So this r represents that exactly, the distance between the vector and the hyperplane. And this is what we're doing here is a projection over the a unitary vector in direction W. Okay, this is just to be sure that this is orthogonal. So we got to this point. In this point, we can replace the numerator. Instead of multiplying or getting the dot product of W, we can write it as the product of the magnitudes of W. And I will show this why this is true. But at this point, just continue with this expression. And we see here that we can cancel out these magnitudes here, and we will get that this R, which is the distance between X and the decision boundary, is simply by moving this to the other side, as we saw in the drawing, y of X over the magnitude of W. Okay. Now, why we can move from here to here? That is simple to show. So consider a generic vector of dimension n. The product W times W is expressed like this: W1 squared plus W2 squared, and so on, Wn squared. And this expression here can be written as the square root of this expression times itself. And this is the definition of the norm of a vector. So this is mainly the product of the norm of the vectors W. So this is the same like this. So in this way, we can see that we can compute the distance from any vector X to the decision boundary. And this expression here, just let me go back, is exactly that we have shown here. Okay, so this is a very important drawing here, a very important plot, where you can see the important concepts of the decision boundaries. Summarizing this, we see that the W vector is perpendicular to the decision boundary. The distance from the origin to the decision boundary can be computed by the negative of W0 over the norm of the parameter vector. And we can compute the distance from any point to the decision boundary by evaluating that point in the surface, in the decision surface, and dividing it by the magnitude of the vector of parameters. Okay, so let's continue. Let's talk now a bit about multiple classes. Consider that K is larger than 2, so we have more than 2 classes. One way in which you can implement a multiple class classifier is in the approach of one versus the rest classifier. So in this approach, for example, suppose that you want to program a classifier of digits. We have 10 digits. Then you will need to create 10 discriminants, one discriminant for each of the digits. And then you can train these K discriminants, taking examples of one of the classes versus the other. Like, for example, you would need to program a classifier that will focus on recognizing zeros. So you will train with positive examples of zeros and negative examples of all the remaining numbers, like 1, 2, 3, 4, up to 9. Then you will need to train a second classifier to detect number ones. So you will have, for that second classifier, you will have examples of ones versus other numbers that are not ones, and so on. So for a 10 class problem, you will need to program or estimate 10 discriminant functions. So this is a practical way to do it, but as it says here, it can lead to some serious ambiguity difficulties, and I'm going to show you that in the next slide. But before that, there's another approach that you can follow instead of one versus the rest. This another approach is one versus one. So you will program, like for example, a classifier that will identify points whether if they are 0 or 1. Okay, so positive examples for 0 and negative examples for 1, and then another classifier for 0 and 2. So you will have positive examples of zeros and positive examples of 2, then another classifier for zeros and 3, and so on. So you will need to consider all the combinations, and that number is this one, k times k minus 1 over 2. This is another way to implement a multiple class classifier considering only binary classifiers. This again will get some ambiguous regions, ambiguity problems, and this is mainly what you can get. For example, if you have a problem with 3 classes, if you use the approach of one versus the rest, you can get a green area like this, where you don't know what is the class that you should assign, because if you evaluate it in one of the classifiers, it would tell you that it is in region 1, so it should be class 1. But if you evaluate it in another classifier, it will tell you that it belongs to class 2. So you don't know if you should assign class 1 or class 2 to this region. And the same happens if you apply the 1 versus 1 approach. It is very easy to show like this, that you can get regions in which you don't know if it should be class 1, class 2, or even class 3. So what would be a better approach than this two? A better approach would be to implement for each of the classes a discriminant function, as we saw before, that would have this form. So if you have k classes, suppose that you are considering 10 classes, then you will need to estimate 10 discriminant functions, okay, j, for each of the 10 classes. And then you will assign a point x to the class ck if that class has the largest evaluation compared to every other j classifier in your set of classifiers. Okay. Decision regions of such discriminant approach are always singly connected and convex. I'm going to explain what is this in the next slide. So these are the regions created by that kind of discriminant classifiers. So all the regions are singly connected and they are convex. Convex means that if you have 2 points from the same region, for example xa and xb, and you draw a line between these 2 points, then every point in that line will be in the same region of these points. So in this region, for example, in any pair of points that you can imagine here, and you draw a line between those points, every point in the line that you create will remain in region K. And the same happens for every other region. So when you implement your multiple class classifier using this approach, you are creating these kind of regions where there are no ambiguities. And this can be shown very easily. So consider these 2 points, xa and xb, both in region Rk. Any point x circumflex here, like this one here, can be expressed as a linear combination or an interpolation, let's say, between xa and xb. And you write that this way: lambda of x, so x circumflex will be some portion of xa, some portion lambda, plus 1 minus lambda portion of xb, where lambda in this case is between 0 and 1. So we are simply interpolating between xa and xb. So since our discriminant is linear, then we are sure that this is true. So the evaluation of our x circumflex in the model K equals the interpolation of the evaluation. So we can evaluate xa in our model K, multiply that by lambda, plus 1 minus lambda times the evaluation of the other point xb in the same model K. So this is also true. And because both xa and xb lie inside region Rk, then it follows that the evaluation of xa will be the largest one, so it's larger with respect to every other j, different to k, and the same happens with xb. The evaluation of xb in our model K is the largest one compared to all other j models, where j is different to k. Hence, this evaluation y of x circumflex is the largest one with the model K than compared to any other j model for that same point. So this evaluation is also lying inside Rk. So this is the proof that if you define your multiple class classifier using these linear discriminant functions, you won't have ambiguity regions. So Rk is singly connected and convex. Now, in this plot, we are seeing what is the difference in the performance of a classifier using least squares and another classifier using logistic regression. If you remember, we said that to go from linear regression to classification, we wanted or we needed to add a nonlinear function, which was the sigmoid function, and we created the logistic regression algorithm. But we said, okay, we can even apply the linear regression because the outputs of the model is going to be 0 and 1, and our linear regression can output that. But we said it seems to be a good idea, but in reality that's a bad idea, because you can find very easily examples where this doesn't work, and this is one of these examples. If we were to classify this and you implement your linear regression algorithm, which in this case is the magenta curve, so you see the magenta curve, and the logistic regression is the one with in green. So both results are good in this, like in a perfect binary classification problem. But if you add some subset of points that are over here, then you can see that the linear regression, the magenta line, changes because it is trying to get closer to the points, because that's what we were solving in linear regression. We wanted the curves to get close to the points. And in the linear regression, you see that it is robust to this kind of sets, because in this set, what we're simply doing is, I just want you to find a line that will separate the points. So every red point will be up this line, in the upper side of this line, and every blue point will be in the other side. And that's mainly because here the least squares is solving what we call the maximum likelihood with some Gaussian assumptions. So assuming that the points are drawn from a Gaussian distribution, okay, and this is highly sensitive to outliers, unlike logistic regression. So what is this Gaussian assumption? So in the maximum likelihood, we assume that points that belong to the same class, like for example the red points, were generated from one Gaussian distribution. That in this case, if we could plot like the contours of a two-dimensional Gaussian, we will get an ellipse like this. And if you would do the same with the blue points, you want to put all the points inside as the same ellipse, then the ellipse should be something like this. Okay, and this is the way that linear regression is considering the points. So linear regression is drawing this straight line to try to be as close as possible to the red and to the blue points in the case of the Gaussian normal distribution. So this is the reason why linear regression fails very easily when you apply it directly to solve a classification problem. So it is much better to use nonlinear transformation like the sigmoid function and work with logistic regression.